the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosines River College in Sacramento, California. This video is for linear algebra students who are going through orthogonality and least squares problems. So far, if you're watching my video series, you should be familiar with the inner product and the length of a vector and how to compute that. In this video, we're going to talk about what it takes for vectors to be orthogonal to each other. Specifically, we're going to talk about the definition of orthogonality. And before we get there, let's go ahead and derive something here. Consider the following graph and derive a formula relating the angle between vectors and their norms. Now, if you've gone through Calc 3, you already know the punchline to this. However, I will still derive it here. So we're in R squared, not that the resulting formula that we get is restricted to being in R squared. We could work in R cubed, in R4, and so on and so forth, but really deriving a formula is much easier in R squared. And we want to build a formula relating this angle theta, and that's the lowercase theta right there, to the norms of these vectors right here. Again, this is assuming that you've watched my video on norms or that you know what the norm or the length of a vector is. The first thing we're going to do is use the law of cosines because, well, the law of cosines would relate that angle theta to those three sides. Solving for this guy right here and dividing both sides by 2, we would get the following. Now, technically, you can go ahead and divide both sides by the magnitudes of u and v, but I'd like to keep fractions out of it for a little bit until we need them. So instead, because we're working in R squared, we can actually write these magnitudes right here, the magnitude of u being squared and the magnitude of v being squared, as a sum of squares of the components of those vectors. Remember, the magnitude of a vector is the square root of the sum of the squares of its entries. So if you square that vector, well, the square root's gone. And so you could see from what we have in this equation right here, that if we allow u to equal u1 and u2 and v to equal v1 and v2, then we get these relations right here, that u squared, the magnitude of u being squared, is just the first component or entry of u squared plus the second entry of u squared, and likewise the same is true for the magnitude of v being squared. And we can also do the same thing for the magnitude of u minus v being squared. Now, obviously that's a little bit messier, but we could square that out and clean it up. If we do that, we get the following. Now you see, that equation actually starts right here, that we're picking up where we left off. We have the magnitude of u times the magnitude of v times the cosine of theta equals 1/2. And then previously we had these nice magnitude notations being squared, but here, this is their component version. And if you clean this up quite a bit, you'll get this right here. Obviously the 2's will cancel beautifully, and we get to that. u1 v1 plus u2 v2 we know is the same as u dot v, because again, those are two-dimensional vectors. So we have arrived at a formula relating the magnitude of those vectors u and v to the angle between the vectors and the dot product of those vectors. This is essentially the formula we derived, and that is a theorem. Notice in the theorem how I have it written, I mention here that theta is restricted to being between 0 and pi. And that should make sense geometrically. If I have two vectors and I want to know the angle between them, well, if that angle opens up to go beyond pi or 180 degrees, then I'm not going to measure the angle this way. Instead, I'll measure the angle the other way. So no matter what, the angle between the two vectors is always going to be between 0 and pi radians, or 0 degrees and 180 degrees. Although you should know, most of the world operates better in radians. Another significant reason as to why we prefer that angle to be between 0 and pi is because often you're going to deal with the cosine inverse here, and the cosine inverse only returns angles between 0 and pi. So again, another good reason to restrict the angle. Now, normally I would follow that up with an example. However, the real examples begin after we get this theorem under our belt and after we define something. But let's get the theorem going here. We're going to let u and v be non-zero vectors of the same size. And when I first read this, I even wrote this theorem down myself. But when I read the same size, I thought, wait, hold on a second. Do they have the same magnitudes? Is that what we're saying? No. They're in the same dimension. In other words, u and v are both in Rn. They don't have to have the same magnitude. They just have to be from the same space. That's what really that should say. Anyway, u dot v is equal to 0 if and only if the angle between those two vectors is pi over 2. Now we happen to know that if u and v are both 0, then u dotted with v would be 0. So that's not the case we're talking about because we're assuming u and v are non-zero vectors. Let's just run through the proof very quickly. We're going to let u and v be of the same size. You see what I'm saying? U and v are in Rn. And suppose both are non-zero vectors. Well, u dot v is equal to 0 if and only if you divide both sides by the magnitude of u times the magnitude of v, well, that should be 0 as well. Both of those equations imply each other. But we happen to know something about this left-hand side of this equation. That is true if and only if the cosine of theta is equal to 0, again because what we've written down here. And note, theta is between 0 and pi. However, that's true if and only if theta is pi over 2. So let's read this forward. If I told you that u dot v is 0, then you would say, well, I agree. Then if you divide both sides by a non-zero number, u dot v divided by that non-zero number should still be 0. And then you say, well, we know what u dot v over that magnitude or product of magnitudes is. We know that's going to be the cosine of theta, the angle between them. So saying this is the same thing as saying the cosine of the angle between them must be 0. But if I told you the cosine of an angle is 0, where the angle must be between 0 and pi, your only choice for theta is pi over 2. Going backwards, if I said, I'm handing you an angle of pi over 2, you would say, great, that means the cosine of that angle is 0. By the way, that angle is between 0 and pi. And then you would say, well, if that angle is actually the angle between the two vectors, u and v, then I can trade out the cosine of theta for u dot v over the magnitude of u times the magnitude of v. So this equation must be true. But the only time a fraction is 0 is if its numerator is 0. So I've proven both directions. But the punchline is this, and something that we need to pay attention to right now. If you have non-zero vectors, and if the angle between them is pi over 2 or 90 degrees, then you know their dot product has to be 0. And this presents something that we're going to use quite a bit, because if you think about, for example, basis vectors for a space, it would be awesome. You don't need this, but it would be awesome if all of your basis vectors were perpendicular to each other. Now, the word perpendicular is reserved for r squared, but once you jump out of r squared and into r cubed, that word perpendicular really doesn't make sense. So we say orthogonal, because orthogonality can be applied to larger dimensions. It's basically like things being perpendicular, it's just an n space, that's all. So we're going to define orthogonality as the following. Two vectors are orthogonal if their dot product is 0, and their dot product is 0 if and only if the angle between them is pi over 2. That might make sense to you in r squared, but once we get to r cubed and r17 and stuff like that, an angle between two vectors starts to lose its meaning. But not really, because you're standing or sitting in 3 space right now. Just grab a pen and grab another pen and just put the tips of those two pens together. It forms an angle between those two pens, even though they're sitting there in r cubed. And if you want that angle to be 90 degrees or pi over 2, they would then be orthogonal. Technically not perpendicular, but orthogonal because you were in 3 space. So let's now put this to use. Determine if these two vectors are orthogonal. Remember, to be orthogonal, their dot product must be 0. I don't actually need to find the angle between them. I just need to show that the dot product of these two vectors is 0. That will imply the angle between them is pi over 2. And there we can see the dot product is actually 0, so therefore x and y are orthogonal vectors. Now again, the whole purpose really of playing with orthogonality, well, there's several purposes, but the one that we can visualize right now is so that we can create a basis for a space where all of our basis vectors are orthogonal to each other. It just makes building vectors within a subspace easier when you have orthogonal vectors as your basis. But there are many other advantages for having orthogonal vectors, or a set of orthogonal vectors. And before we get there, we're just going to throw in a couple other theorems in this video, and then we'll call it quits here. And the two other theorems in this video are very quick. They're kind of easy to understand. The very first one is that the 0 vector is orthogonal to every single vector out there. And it doesn't take much brain work to do it. If u is any vector out there, then u dot 0 is going to be 0. So therefore, the 0 vector is orthogonal to every single vector. And that usually is only useful in proofs, to be honest with you. Even though it's a very easy theorem, it's not super powerful for use in application. The last theorem, though, that we're going to use in this video is the Pythagorean Theorem. Two vectors u and v are orthogonal if and only if the magnitude of u plus v being squared is equal to the magnitude of u squared plus the magnitude of v being squared. We happen to know that the magnitude of u plus v being squared is the same thing as u plus v dotted with u plus v. We have a theorem that tells us the magnitude of a vector being squared is just the dot product of that vector with itself. But we have another theorem that allows us to do the distribution of these vectors. So all I'm doing here is I'm taking this u plus v on the back end and I'm distributing it to each of these two vectors right here. Then I go ahead and do another distribution process, just distributing this u across to each of these and this v across to each of these. And we happen to know that the dot product has the commutative property. So u dot v is the same thing as v dot u. And again, a vector dotted with itself is just the magnitude of that vector squared. Well, this doesn't look like where we want to end. Remember, we want to end with the magnitude of u plus v squared is equal to the magnitude of u squared plus the magnitude of v squared. But this silly little 2 times u dot v is getting in the way. Oh, wait a second. We were told one thing. U and v are orthogonal, which means u dot v must be 0. And this happens, like I just said, if and only if u and v are orthogonal. So there we go. That is a nice, clean, easy proof of the Pythagorean theorem using vectors. Now there's nothing else that I have for you in this video because this is just an introduction to orthogonal vectors. The main thing that you want to take away from this video is that two vectors are orthogonal if their dot product is 0, and orthogonality is just the n-dimensional version of perpendicularity. And that's about it. So I hope to see you in future videos, and I hope you have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.